This is the written work of Harper Armstrong. I have permission to use their work in my video, and my answer to all topics 1 through 4 would have been the same. So for Harper's first problem, she did a tilted pipe that had a manometer measuring the pressure difference between point 1 right here and point 2 right here. So hydrostatics is involved because this delta H, you use the density and the gravity to find this change in pressure, because the manometer is going to be used to find that change in pressure. The Bernoulli equation is used because this pressure right here and this pressure right here, as long as the velocities and the heights can all be modeled through the Bernoulli equation. So this Bernoulli equation right here and this hydrostatic equation right here are both used in this problem. First, you have the modified Bernoulli right here, which has a change in pressure, and then you also have this change in pressure related to hydrostatic height, which is where hydrostatics comes into play. The significant assumptions made is that the pipe flow is steady and compressible, and that the work and friction are not neglected. Also that there's no friction work present, so there's no turbo machinery, and then also air can be assumed to be an ideal gas, and also the elevation gain between the two manometers is negligible in this problem. So the only properties that were needed to be looked up was the density of the fruit syrup, which is the manometer fluid, which is used in the hydrostatic equation, and then of course the gravity constant is 9.81. So the solution to this problem first starts by finding the velocity. You take the cross-sectional area, and because we have the volumetric flow rate, you find the velocity off of that. Then you then find the density using the ideal gas equation, because air could be assumed to be an ideal gas. And then you have this simplified Bernoulli equation where you have a delta P and the kinetic effects, the friction, and the density, all to find the change in pressure. All this change in pressure can then be chalked up to the change in fluid height, and this is found right here to be 0.076 meters, or 2.99 inches. For Harper's second problem, she had a bug floating on wine, which had the Archimedes law involved, and also the macroscopic momentum balances involved. It was Archimedes law because the bug is going to be floating in this liquid, and it's going to be displacing some sort of fluid and a volume of that fluid, but also the bug starts flying away and starts crying, and that involves the macroscopic momentum balances as the bug starts losing mass. So the key equations in place here is in the first part, when the bug is floating, you have the weight bug, which is a force, the density times the area times the height times the gravity force, but then once you have the weight of the wine displaced, which is going to be the buoyancy force, acting in the opposite direction of the weight. In the second part of the problem, when you have the macroscopic momentum balance, you have this equation right here, which can sum up all macroscopic momentum balances. Some important assumptions to make is that the buoyancy force is going to be equal to the weight force because the bug is floating on top of the water. We also know the bug is a perfect rectangle. We also know that the density of the wine and bug are going to stay constant, and there's also no change in temperature based in the location of the fluid. There are no other properties cited other than the gravity force here, and the dimensions of the bug we've already been given. We do know the bug is going to be floating on top of the wine, so we can set the weight force equal to the buoyancy force as seen here. Then, dividing and simplifying, we can find that the depth of its submerged is equal to the ratio between the density of the bug and the density of the wine times the height of the bug. All of this considered, it simplifies down to this. Now, because we know the depth at which it's submerged, we can use the cross-sectional area times that depth times the density of the liquid to find the buoyancy force here. The last part can be modeled with a momentum balance. This can be simplified because we know that there's no mass flow rate going in, and we know the only force acting on it is the gravity force. We know the change in velocity over time is acceleration, and this is also going to be the mass flow rate. This is the resulting equation, and solving for ma, we get that the ma equals negative mg. That means the acceleration is negative gravity. This means that the force acting on the bug will be equal to m times a, or this. Here are the references that Harper used for her problems.